So in this session, we're going to see how to manipulate formulas in Sole.jl, how to compose them, parsing them from string, and like randomly generating them, checking them on logical structures, that is interpretations, both at the propositional and at the model level. Yeah. So as I was saying, there is like in the most abstract at the most abstract level, we have atoms that are just names, right? Like P, Q, R. But in general, Sole.jl is built in a way that you can wrap anything you want inside atoms, and as long as you have structures that can tell you the truth of those atoms, you're going to be fine, and you can use Sole.jl for speaking your own language and for checking formulas on the structures that you want. Okay, so if you want to use Sole.jl, just type using Sole.jl in the Julia REPL. Just add it as a package, and then using Sole.jl, and then let me just say, so I've prepared three blocks. One is about propositional logic, but it also showcases how you can play around with formulas and check them. Another one is actually talks about what we call scalar interpretations or tabular interpretations. That is the case where your your logical instance is actually a vector of numbers, and you check formulas where the atoms are in this form. Okay, so Sole.jl does not have this, because Sole.jl is about abstract structures that do not even talk about numbers, about scalar numbers and comparisons, thresholding. It gives you the tools for composing concepts via logical connectives, and it gives you algorithms for model checking, but you decide the language. Okay, so in this case, I'm using, in this second block, I will be using Sole.jl to instantiate my own type of atoms, condition on an attribute, which is essentially something like this, and my own interpretation, and I will check formulas on these things. This is not in Sole.jl because we only care about this when we do symbolic learning. But Sole.jl can also be used in other contexts if one wants to. Okay, in contexts where you don't play with numbers. Does it make sense? No? Any question about this? Okay. Okay, and then we're going to lift that at the model level by playing with graphs, essentially. And then we're going to put the two things together with actually an exercise that if we have time we can do together. Otherwise, I'm leaving it that to you, where we put the two things together, and the exercise is about actually creating a structure, a model structure with scalar values in the worlds like the ones that Guido presented to you earlier, and see that you can check such formulas on those structures. Okay. Okay. So as I said, okay. So if I using Sole.jl, and then I can instantiate an atom as something. An atom is just a wrapper for any value. I can put anything in an atom, right? So let's do with strings for now, because I want to speak a language of strings. I can compose strings, for example, by using a conjunction, okay? And this gives me tree-like structure in general. In this case, a syntax branch. I can also, of course, compose more complex formulas like this. Whatever I type here is something that you can type in the Julia REPL. Okay. So you can build formulas by composing them in this way, and each of these is actually. So what is this thing? This is okay. What is it? Type of this. This is a logical connective that is only defined by. It's just a symbol. Okay, it's a symbol. The end. And actually, all of the logical connectives that we're going to see today are of this kind. But then when we get to more complex connectives, like the ones that Guido showed, that have relations, relation 1, relation 2, those are not going to be defined by symbols only. And these are names, and these are objects of type named connective, but I can also use them as functions. So essentially, this is a shortcut for something like this. So you can use these to compose formulas, okay? And so as I said, these have a tree-like structure, which, by the way, you can also navigate. So, for example, I have here this formula phi, right? It's a formula. So what is a formula? Formula in SoleLogics is an abstract structure which it's an abstract type for all kinds of things that you can translate to a syntax tree. So these tree structures, where at each node you have a logical connective or an atom, or a little more than that, we'll see. So for example, both P, that is an atom, and phi, which is a syntax branch, are formulas. Okay, this is a syntax branch. What do I mean? It's something that has a root with an end in it, and then two children. Okay, and you can navigate through it. For example, you can ask for the token at the root, which is the connective that was used to compose these two formulas. And the children is a tuple, or sort of like a list of the two children, right? So I can navigate through this structure manually, by asking, for example, in this case, the only thing I can do is to ask for the first children, for example. Here I'm creating a method for negating a formula. I'm going to use the method which simply negates the formula. This is very simple. I'm just doing this for in order to familiarize with the Julia syntax. Like I'm creating a method for the negate formula, which I then provide the formula, and it gives me that formula. But so it takes the syntax tree and it makes a new syntax tree where the root is the negation, and it attaches the tree. Make sense? Too easy? Perhaps too easy? Should I go faster or slower? Faster. Faster. Fast forward. Okay. I can get a string representation of formulas. Okay. I can parse formulas from strings. So yeah, we have this syntax tree function and this parse formula function, which are one the inverse of the other. And by default, parse formula parses formulas that are strings. So if I do this, essentially I get the same formula that I showed you earlier. But say and if I want to have different things at the leaves, it doesn't really do that by its own. For example, if I do this and then I see, I'm going to look for the first children. You see, in the atom it has a string, but maybe I want an integer in it, and there's a way. But and you can look at the documentation if you want to do fancy things. SoleLogics is quite well documented if you want to play around with it. You can find the documentation if you go to the GitHub repo and you go here. There are also some hands-on. We're working on a section which goes through modal logic in the same way that Guido did, but with SoleLogics in mind and using SoleLogics. So I guess this does not look too useful at this point. So I'll go. I'll go over a little faster. So if I want to, for example, in Julia, there is this multiple dispatch programming model, which for which you can provide many methods for the same function, of course, and and each method you can say that it is going to capture a specific kind of object, right? So in this case, for example, I'm writing my own my own function that translates a formula into a string representation, which is also what I did when I showed you this earlier, like the translation from a formula to a natural language. Okay, so you can do this. You can recurse through the tree, of course, by writing these methods. Yeah, for example, when I maybe I want to say, maybe when I want to say not phi, what I want to translate it like it's not the case that, and then I'm going to say whatever phi says. Okay. Okay, that's it for the formulas for now. What about the interpretations at the propositional level? At the most abstract level, we don't have numbers in the interpretations. We don't have attributes. We just have names, P, Q, R. So interpretations are actually mappings from P, Q, Rs, from atoms to truth values. Okay, for example, I can say that my soul is not mortal, but it's alive. So P, yeah, so essentially it's a dictionary assigning truth values to the atoms, right? And my body, actually, it's both mortal and alive. I can check an atom on an object like this. There's a checking algorithm that, as Guido mentioned, is quite straightforward. I can check more complex formulas. Actually, since these are mappings, I can do a lookup and ask for the specific truth value for a given for a given atom. Okay, so in this case, for example, I ask to my soul whether it's alive. No, wait, my soul. What does this do? Oh, apparently I said that my. Okay, this is to be mortal, I think. Okay, so. Okay, I don't know what's happening. I think I'm getting. Yeah. Anyway, my body has this truth value for the atom Q. Okay. What is a truth value, though? Well, I mean, so far it's a mapping from these names to Boolean values, like true and false, right? But actually, internally, we don't deal with these values because Sole logics can be extended to logics where things are not either true or false, but they can be probabilistic, or they can even go. You can get quite abstract, and the infrastructure is there for these kind of extensions. And we're going into a direction where we're also studying the extension of the symbolic learning methods that we have to so-called fuzzy logics. But so if we stick with a Boolean logic, we're going to have truth values which are essentially either this or this, right? And these are what? This is just stop, but it's also, yeah, as it says here, it's a formula. It's a formula of a specific kind. It's a truth value. It's something that can be at the leaves of a formula. Same as the atoms, but it's a constant, so you always know whether it's true or false. I mean, you always know its truth value. In fact, itself it is its own truth value. So essentially, the connectives that we have in propositional logic, which are these, and by the way, in Julia, you can use Unicode characters, which can be quite handy, and you can do things like this. Top, but use the LaTeX shortcuts. You type the thing and then you hit tab, and it types the symbol. But if you don't want to work with those, we also have aliases. And so all of these, we call these the operators. And the operators that are not truth values, we call them the connectives, because you use them for composing formulas, larger and larger formulas, okay? When you check a formula on interpretation, what you're actually doing is you want to know the truth value for that formula, right? So what we have is oh wait, now I'm gonna do something here because I changed this function. So okay, let's go back to this. So for example, say I have that function which asks whether I'm both mortal and alive. Okay. Okay. Apparently, yeah, my soul is not, because it says it's, yeah, the truth value for that formula is false. So if I have my soul, which is the data, you know, my grounding, the thing that I know, and this is something else that I know, but this is my knowledge. This is my data, and this is my knowledge. Essentially, this is what symbolic modeling, and symbolic learning is about. I can interpret this formula on the propositional interpretation like that, and this also, and yeah, I can also use this nice syntax when I do a lookup. So I can use this for asking the truth value of atoms, but also of formulas. And internally, it's going to use the interpret algorithm, the one that, you know, is simple at the propositional level, not so much at the model level. And that also works if you have unknown. This is interesting. This also works if you have if your formula has atoms which your propositional interpretation does not have an answer for. Okay. So my interpretation here has an answer for P and Q, but it does not have an answer for this new atom that I just made up. So the best that the interpret algorithm can do when you look up is to simplify this whole formula using the information that is in the interpretation. So in this case, for example, I know that apparently my body satisfies this phi. So when I do the interpretation, what I get is the atom, and the atom for my body, apparently, the atom has the same truth value. I don't know what this atom means, but whatever it means, it will yield the same truth value as the composition of this formula. Because I know that for body, this is true. So true and something means something, essentially. Okay, so there are such kind of optimizations, let's say. Okay, I can generate random formulas. This is interesting because we will be using this for as a first form of learning in a way, because for example, if you have a data set of interpretations, if you know the language that they speak, you can generate random formulas and only keep the ones that are good. For example, this can be a first learning algorithm, right? Okay, so for example, here I can generate the random formulas. All I need to give is the set of connectives that I am going to use. For example, if I use the propositional connectives, I think this set counts either 3 or 4 connectives that are the conjunction, negation, implication, and disjunction. I have to give it a set of atoms, an alphabet, right? That is the one that it's going to use. And by default, yeah, it doesn't use truth values. Doesn't put truth values at the leaves. So yeah, this is a formula a random formula, and I can also have there's this normalizing function which attempts at simplifying a formula, because there are, you know, De Morgan rules, some rules that you can apply for say you have for basically doing something similar to what I did here. Like if I know that this formula checks top, essentially, I mean, I can remove this part of the tree, and this atom has the same semantics, right? So I can get a shorter formula with the same meaning. So for example, this is the same as this, which if I were to read it out loud, it's more intuitive. There are many alternations between negations, ands, and ors, which can be convenient. So yeah. Exercise 1, which I mean I'm not asking to do now, but check many randomly generated formulas on an alphabet P and Q on both soul and body. Do soul and body have the same probability of satisfying a generic formula? Can you estimate this probability? So yeah, this is going towards the idea that we can learn formulas this way, right? By the way, I don't have an answer on this. It's probably very, very simple. I mean, there's probably a very simple answer. So if we want to get closer to learning, we have numbers, right? So our atoms are of this kind, and our interpretations are vectors of numbers, okay? So let's see how we can extend Sole logics right now for dealing with this kind of data. So first of all, there's a thing that I define that is a scalar condition on an attribute. That is the thing that I'm going to wrap into my atoms. And if I have a propositional interpretation, I can always say if that is true or not. Okay, so these are objects which, by the way, if you want, if you put them in formulas and you ask for the syntax string for the formula, that is the string representation, you want them to look like this in the formula. Okay, so this is what I'm doing here. Each condition only has the index of the attribute you want to perform the comparison and the threshold value. I define my tabular interpretation as a structure which is a subtype of propositional interpretations, which in Sole logics are called abstract assignments. And the only thing, I mean, all a tabular interpretation has is a vector of real numbers, okay? And the only thing that I really need to tell Sole logics if I want to interpret formulas on these structures is how to interpret atoms, because I know the semantics for or, and other connectives. By the way, I can also make up my own connectives, but that's another story. So I tell Sole logics how to interpret my atoms. So an atom, essentially the truth value for an atom on a tabular interpretation. In order to get that, what do you do? Well, you actually perform the comparison, right? So you look up in the tabular interpretation, you look up the value for the attribute, you compare it. In this way, I didn't use both. I said, let's fix less than, okay, as a condition to make it simple. Yeah, and then I take the threshold of my condition, I compare it, and if it's true, that top is my truth value for this atom. Otherwise, it's bottom. So now I can. Is this clear? Okay. So now I can, for example, generate. Okay, this is a random interpretation, just a vector of four values. I can make up my own 44-element alphabet, which is a vector of atoms, which are the combination of, you consider all four variables and then some thresholds that are between 0 and 1, okay? So apparently it comes, I get a 44-element alphabet. That's a vector of atoms in this case. Well, I can interpret each one of them on the interpretation, okay? I'm gonna get a bunch of truth values. Some of them are going to be false, some other are not going to be false. But then, most importantly, I can feed this alphabet to the random formula generator, okay? Which just shoots out syntax trees with these things at the leaves. And I can interpret each one of these on my interpretation. I can, yeah, so here I generated 10 of them. And for example, the first two checks true, the third one does not, okay? Yeah. right? Does it make sense? Exercise 2. Check many randomly generated formulas on many randomly generated tabular interpretations and store the formulas that satisfy the highest number of instances. Okay, we're getting to, I mean, with the code that I just wrote, I could instantiate many random interpretations, many random formulas, and I mean, I can generate many formulas and only keep the ones that satisfy the interpretations. I'm not sure what will be the common pattern of the formulas that are going to satisfy all of the interpretations in that case. Maybe it's not as simple as an answer. Okay, so at the model level, essentially, in Sole logics that is at the most abstract level, you don't check formulas on propositional interpretations, but on directed graphs of propositional interpretations. Okay, so there's the directed graph, and then our Kripke structure essentially it's a coupling of a directed graph, which is essentially it's a graph. I can instantiate it as a graph. And in Sole logics and in the literature is called a frame. A Kripke structure has a frame, which is only the structure of the worlds and the relation over the worlds. So for example, here I have 5 worlds, and this is for example, 2 and 3 are accessible from world 2. I'm using this word accessible, but it has the same meaning as reachable when from the slides of earlier. So for example, if I instantiate a frame, okay, in this case an explicit crisp unimodal frame, because what you saw is actually a very specific kind of frame. It only has one relation. For example, it is crisp in the sense that the logic is not fuzzy. Atoms are only either true or false. So it's a specific kind of frame, and you can also have more complex frames. In fact, Sole logics does. But in general, what you can do with frames is you can enumerate the accessibles from a frame, from a world of the frame, and that is going to give you a vector, but in general, an iterator or a generator, something that you can iterate and list all of the worlds that you see. And of course, this is what you need when you want to check a formula, right? When you want to check if a formula is true, you look at you were looking at the structures, at the graph earlier, and you would traverse the graph. So a Kripke structure actually is a frame plus a valuation, what I call a valuation, which is a mapping that assigns each world with a propositional interpretation like body and soul. Okay, so on some worlds P is going to be top, on others is going to be bottom in this case. So I have my Kripke structure here, okay. I can do the same that I was doing earlier. So I can generate a random formula, but this time a model random formula. All I need to do is to change the connectives that I give my random formula generator, because a formula is just a syntactic structure, right? So of course the same algorithm is going to work. Oh, sorry, that's another thing. If I feed, of course, it's going to work if I feed just 2 new symbols. Okay. So in this case, it came out like this. It says, all worlds that I see, it's alive implies it's mortal, or it's not true that it's alive implies it's alive. Yeah. By the way, this can surely be simplified. For example, I'm sure if I call the normalize function with this, it's going to probably get rid of this, or maybe it checks. Yeah, probably it will get rid of this. And so, as checking formulas is relativized to worlds, now I'm not I'm not doing this. I'm not checking the formula on the whole structure, but I'm checking the formula on, say, all the worlds in the structure, one by one. So in this case, I find that the formula is false on the first world, but is true on every other world. Okay? Exercise 3. I think it's the same. Yeah, it's the same as earlier, but just at the model level. Exercise 4. Define a structure for representing a model interpretation on scalar variables. You can on scalar variables. Okay, so this is the same. The thing that I was doing at the propositional level, I can do at the model level. That is towards the idea that we're going to learn from Kripke structures that have numbers on the worlds. I'm going to, so we want to define an object like that, and we want to generate formulas where the atoms are scalar comparisons, but the atoms have, but the formulas have boxes and diamonds, so yeah. You can see if your solution works by running the cell below, which instantiates. Okay, yeah, I think if I prepared it in a way that if I put the right code here, the last cell is going to generate many random formulas and basically show how they check on each world of the structure, right? So as before, the only thing I need to define is the model interpretation, which in this case, it won't be a subtype of abstract assignment, but it will be a subtype of abstract Kripke structure, because at the model level, you need Kripke structures. And in a similar way, my interpret function is going to accept a world which was not at the propositional level. Okay. And I guess the solution is very trivial. I don't know. So okay, let's conclude with this. I have the solution here, but wait, was there something interesting in the solution? I don't think I don't think there was anything specifically interesting of the solution. Model interpretation is essentially a frame. Okay, yeah. So I have a frame, which is my graph, and I have something that assigns vectors of values to each world, right? So essentially, yeah, I have a tabular interpretation on each world. Right, okay, yeah. So if you're interested, I left the solution on the repo as well. And that concludes the session.